Prepare for battle.
In case you're wondering, it's in the bag.
Never in the long history of the Earth has there ever been a battle more in the bag than this one.
30 seconds to battle.
Their suffering is about to end.
The battle begins.
Just expressing myself.
You get nothing.
First blood.
With the fishes.
They're gonna regret letting me have that. Not today.
My mark cast upon the tides.
That should
Dire's
help.
top tower is under attack. Dire's top
Double
tower
damage.
has fallen. Radiant's middle tower is under attack. Dire's bottom tower is under attack. Radiant's top tower is under attack.
Anti-venom.
Radiant's top tower is under attack.
Anti-venom.
Dire's middle tower is under attack.
Tide.
The battle is
Prepare
ours!
for
Victory
battle.
is assured! This one is in the bag!
"30 seconds to battle.
It's never been more in the bag.
The battle begins.
Denied.
Dire's courier has been slain.
Heal us.
Radiant's top tower is under attack. Radiant's top tower is under attack. Radiant's top tower has fallen. Radiant's top tower is under attack. Radiant's middle barracks have fallen. Radiant's middle tower is under attack. Radiant's top tower.
Radiant's middle barracks has
Radiant's
fallen.
middle barracks have fallen. Radiant's middle tower is under attack.
Regeneration.
Radiant's top has been slain.
Behold the Scourge of Icerack. On!
Prepare for battle.
I thought as much.
This
I'll not
one is
argue.
in the bag, and not
There's a lot more we could do
Swift
with
as the
Beg,
wolves
if you
of
ask
Ice
me.
Rack.
Which nobody does. Because why on earth would
It
they?
is in
We're not exactly talking about
Let's
geniuses,
go.
are we? Honestly, there's a real lack of imagination around here.
Swiftly!
Thirty seconds to battle.
Here I come! Yes! Forward.
first blood. The
I
bone
move.
harvest begins.
It's all fun and games until I'm under attack!
Indeed.
Into the breach! Agreed. To battle!
My bones, men. Take a knee, peasant.
Faster! Agreed. Let's go. Into the breach. Here I come. I thought as much. I move. Yes. I'll not argue. On. Forward. To battle. Indeed. Swiftly. I'll not argue. Forward.
So what if I swagger?
I thought as much. Agreed. Faster. Into the breach. My eye spites deep. Yes. On. I move. To battle. Indeed. Swiftly. Here I come. This'll come in handy. Let's go.
No.
Indeed.
Double kill.
I move. Lena. Agreed. Fangs of ice. Yes. On. Swiftly. you go. Brr. That's faster. Ah! Here I come. Ice, take you. I'll not argue. Forward. Let's go.
Very well.
I thought as much. Here's ice in your eye. I'll freeze you fast. Into the breach. You again. To battle. Now, nobody wins. On. Forward. To battle. Let's go. I'm under attack. Faster. Swiftly. Swift as the wolves of Ice Rack. I'll not argue. You. I move.
Dominating.
Here I come. Agreed. Indeed. Yes. I thought as much. You again. Into the breach. On. Into the breach. Here I come. I move. Indeed. Forward. I thought as much. Let's go. I'll not argue. Faster. To battle.
Your top tower is under attack.
I'm under attack. Lena.
Sorry, sister, but you needed thawing.
You only live ice. Swiftly. Agreed. Yes. Indeed. Let's go. Faster. Ah! I move. Swiftly. Yes. On. To battle. It's not time. I've got goosebumps. Attack. Agreed. Into the breach. Forward. I'll not argue. I thought as much. Here I come.
Stolen.
Forward. I move.
Regeneration.
To battle.
Your middle tower is under
The ice
attack.
wolves bite. Faster. I always was the good one.
Burn, baby, burn.
Don't call my headstone just yet.
I thought as
Your
much.
bottom tower is under attack.
Agreed.
The enemy's
Swift
middle
as the
tower
walls of
has
ice.
fallen.
Indeed. Swiftly. Here I come. I'll not argue. Into the breach. Yes. Ah! On. Let's go. Swiftly.
Dominating.
Here I come.
What are you buying?
To battle.
Enough.
I'll not argue. I move. Let's go.
Outworld. Calling.
Agreed.
Your bottom tower is under attack.
Die.
Your bottom tower is under attack.
Is it cold in here, or is it just me? I thought as much. Yes.
Dominating.
Forward.
Your top
Faster.
tower is under attack. Radiant's courier has been
Thanks,
slain. Your top tower is under attack.
On. Ice, take you.
Your top tower is under attack.
Into the breach. Indeed. On. Aren't you nice? Agreed.
Mega kill.
Not enough for you? Better to burn
I'll not
out.
argue.
Mostly without me.
Indeed.
Your top tower has been denied.
Let's go. Into the breach! Swiftly! Yes! I thought as much.
Don't believe this.
Faster! To battle! Here I come!
Your middle tower is under attack.
I move! Ah!
Your middle tower is under attack.
An end to ill omens.
Swiftly!
Your middle tower is under
I
attack.
thought as much.
Your middle tower has fallen.
Agreed.
The enemy's top tower has fallen. Your middle tower is under attack.
I'll not argue. Faster!
Welcome to the secret shop.
To battle! Into the breach! I move! My eye spites deep. Forward. Indeed. Let's go. On.
Invisibility.
Here I come. Yes. Swiftly. Here I come. To battle. Swift as the wolves of Iceland. Indeed. The ice wolves bite. Agreed. Yes. I thought as much. I move. On. Faster. I'll not argue. Let's get on. I'll freeze you fast. Forward.
To be the key.
Into the breach. Faster. Here I come.
Triple kill.
On. To battle.
Dire structures are fortified.
Yes.
Gold for my master.
This'll come in handy. I move. Swiftly. Let's go. Agreed. I thought as much.
My bones mend.
Forward. Into the breach. Indeed. I'll not argue. Agreed. To battle. Faster. Let's go. I move. Indeed. Swiftly. I'll not argue. Not visible. On. Here I come. You will mature. Into the breach. Forward.
Bad luck.
I thought as much. Yes.
The stone has reached my heart.
The enemy's bottom tower has fallen.
Under attack. I'm burning up.
Nothing brightens up the aeons like a good game of collect the corpse.
Now, nobody wins.
Who put that ground there? I usually have people for this. Preemptive.
Nothing like a little cool down. Forward. Indeed. I thought as much. On. Agreed. Let's go. Swiftly. I'll not argue. Faster. Yes.
My old friend.
Swift as the wolves of Ice Rack. I move.
Stricken out.
Here I come.
Back rot! Aw, mate.
Into the breach. Forward. On. Indeed. Yes. Let's go. Here I come. Swiftly. Into the breach. Faster. Swift as the wolves of Ice Rack. I move. I'll not argue.
Your middle tower is under attack.
Agreed. I thought as much. To battle. I thought as much.
No way!
I'll not argue. Faster.
Dire structures are fortified.
To battle.
Your top tower is under attack. Your top tower is under attack.
Swiftly. Agreed. Yes. I'm under attack. Forward. Breaks. Let's go.
Your middle tower is under attack.
On. Nice.
Radiant structures are fortified. Your middle tower is under attack.
I
The
move.
enemy's bottom tower has fallen.
Here I come. Into the breach. Into the breach. To battle. Forward. Here I come. Swiftly. Indeed. Yes. Faster. Agreed.
Radiant's guardian has been slain.
Let's go. I move. I thought as much. I'll not argue. On. Into the breach. Swiftly. Indeed. I move. Forward. To battle. On.
Roshan
Immortality.
has fallen
Agreed.
to the dire.
Let's go.
So what if I swagger?
I thought as much. Here I come.
invisibility.
I'll not argue. Forward. I'll not argue. Into the breach! Faster! Let's go! Agreed.
Hey, I'm easily distracted.
Let it roll over.
Yes! On! I move! To battle! Indeed! Here I come! Ah! Swiftly! I thought as much. Yes!
There'll always be something worse on the wing.
Your bottom tower is under attack.
Go for my master.
I didn't see that coming. I thought as much. Into the breach!
Illusion.
Here I come! On! I'll not argue. Let's go! To battle!
Double damage.
Agreed!
Just need you to know. You suck.
Forward! Die! Put me out! I'm under attack! I move! Faster! Swiftly! Yes! Forward.
The enemy's middle tower has fallen.
Here I come! I'll not argue. Into the breach!
The enemy's middle tower has fallen. Radiant's
Swiftly.
courier has been slain.
Down you go!
The enemy's middle barracks have fallen.
Indeed. I thought as much.
Your top tower is under
Faster.
attack.
On! To battle! Agreed. Let's go. Into the breach. Let's go. Ah. Faster. Here I come. Fangs of ice. Indeed. Yes. Forward. I'll not argue. I thought as much. On! To battle! Swiftly! I move! Agreed. Into the breach! Indeed. Agreed.
Nope, nobody's down there.
Swift as the wolves of Icerack. To battle. I thought as
Your
much.
bottom tower is under attack.
Faster.
Bounty!
Your bottom tower is
Forward.
under attack. Your bottom tower
Yes.
has fallen.
Here I come. Swiftly. On. I'll not argue. I move. Let's go. I'll not argue.
Your bottom tower is under attack.
Yes. Agreed.
Your bottom tower is under attack.
To battle. Into the breach. I move. Swiftly. Here I come. Faster. On. Indeed. Let's go. Forward. I thought as much. I'll not argue. Here I come. Forward.
sink my blade. Good soil.
Into the breach!
Bounty.
I thought as much. On! To battle! Indeed. Yes. Let's go. Agreed. I feel colder already.
Just keeping it loose.
Drop it.
Next time, I will set surprise assassinations.
Swift, I'm under attack.
I bring the heat.
Forward. I'll not argue. To battle. On. Let's go.
To the oblique.
I move. Faster. Indeed. Nice. Regeneration. Yes. Cold as death.
Shouldn't have trusted your eyes.
It just keeps getting better. Agreed.
Roshan has fallen to the
Swiftly.
dire.
Immortality.
Into the breach. I thought as much. Here I come. On. I thought as much. Let's go. Here I come. Swiftly. Forward. Yes. Agreed. Ah! No!
I need better counsel.
Thanks for standing still.
Your middle tower is under attack. Radiant structures are fortified. Your middle tower is under attack. Your middle tower has fallen. Your top tower is under attack. Your middle tower has fallen.
Once burned, I
Your
shall.
middle barracks are under attack. Your middle barracks have fallen. Your top tower is under attack. Radiant structures are fortified. Dire structures are fortified. Your top tower is under attack. Your top tower has fallen.
To battle! Indeed. I'll not argue.
Gotta keep limber. I was meant to have this.
I move. Let's go. I thought as much. My temperature's dropping. I move. Forward. Here's ice in your eye. On. Indeed. Faster.
I'll not argue. Has fallen.
Swiftly. Under attack. Here I come.
Your puppets are under attack.
Agreed.
Your top barracks have fallen. Your middle tower is under attack. Your middle tower is under attack. Your middle tower has fallen. Radiant structures are fortified. Your middle tower is under attack. Your middle tower has fallen. Your ancient is under attack. Your ancient is under attack. Your bottom tower has fallen. Your ancient is under attack. Dire victory. 10 seconds remaining.
Places, everyone.
It's in
Take
the
the show on the road.
bag!
Prepare for battle.
Getting in gear. Stand still. I just want to try something.
30 seconds to battle.
Who asked you? One gear in front of the other. Nothing would please me more. Cry about it.
This was in the bag the day Axe was born!
Time to break a leg. Time to step to it. Come one, come all. Let me go. I think I can handle it.
You get nothing.
Step right up. What did you say? I'm under attack.
Radiant warrior has been
Get over
slain.
here, you fools. I'm the leader of this show.
Look to your own.
Oh, I got a Denied. Consider this an audition. Cut. wants to be my next audition? My pleasure. What's the ballyhoo? Yes, yes.
First blood. First blood. Have I got jigs on the chins?
I just came up with a new act. My master should have built me with wheels. I'm under attack. Time for taming. Coming soon to a village near you. Get off my stage. Bum ba dum ba dum ba dum ba dum be doo doo. What? No advance? A true patron of the arts. Like a real boy. Pulling up stakes. The knives are real, and the trick is that it's not a trick. Snap too. Oh. Now the real bit. This circus travels. There. Why aren't you watching? Wind me up. And that's our show. Like clockwork. Itchy feet? Perfect. Ah. 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 Just because I say. Proper blocking is paramount. Wind me up. Hey, I'm under attack. Let me go. Come one, come all. Nothing would please me more. Who asked you? Some people call you friends. I call you like a real boy. Hands off. Now, where did I put that apple? Hands off the merch. I'm under attack. I'm the leader of this show. Go on. Throw me on the scrap heap.
Come and get it! Deadly cut-through double kill.
Back by popular demand. This circus travels. Places, people. Step right up. Step to it. Haste. Oh, we do this trick differently. Get over here, you fools. Time.
Over here now.
It's all
Let the fun begin.
getting in gear. pleasure. Proper blocking is paramount.
Mine.
Where do they all fit? Perfect. Cut. I think I can handle it. I must nuke them into a frenzy.
Ah, fresh
Take the
meat!
show on the road. There. The knives are sharp and the tears are clear. Itchy feet. Just because I say. One gear in front of the other. I just had the most wonderful idea. What's the ballyhoo? I'm under attack. It's not torture, it's encouragement, pulling up stakes. Scouting location? Someone is always sneaking around trying to spy. Yes. Ah. I'm the leader of this show. Nothing would please me more.
Regeneration!
My pleasure. Step to it. Getting in gear. Yes.
Get some!
Dire structures
I'm
are
under attack.
fortified.
I feel a certain lack of mind. Why aren't you watching me? Who asked you?
Stupendous!
Places, people. Let me go.
Your middle tower is under attack.
Very well.
Itchy feet. Come one, come all. Proper blocking is paramount. Take the show on the road. Perfect. I think I can handle it. Just because I say. Step right up. Pulling up stakes. Like a real boy. Scouting location.
Those who called Axe a bear of a man have never...
There. Wind me up. This circus travels.
Your top tower is under attack. Radiant's courier has been slain. Your top tower is under attack.
One gear in front of the other. Take the show on the road. Step to it. Pulling up stakes. Who asked you? One gear in front of the other. Hey, look over here. I told you not to step on my lines.
You mega kill.
Itchy feet?
Your top tower is under attack.
This circus
I'm over here.
Your top tower is under attack.
Standing ovation. I think I can handle it. Come one, come all.
Boy, fresh mate.
Your top tower is under attack. Your top tower is under attack.
There.
Your top tower is under attack. Your top tower has fallen.
What? No advance? Nothing would please me more. Wind me up. Like a real boy. Ha. Oh, let me go. I'm the leader of this show. Oh, finally a fitting muse.
Illusion.
Step right up.
Your bottom tower is under attack.
Just the place. What's the ballyhoo? Oh, you're going to miss the best part. Yes, yes. Scouting location?
Spring pop.
I think I can handle it. Where there's a wind. Perfect.
Unstoppable double kill.
Catch.
Middle tower is under attack.
Taste the axe.
Dire structures are fortified.
Just because I said. Dance. One gear in front of the other. What? No advance? We'll use those in the pit. My pleasure. Proper blocking is paramount. There. Yes, yes.
Stupendous.
Do me a favor.
Your middle tower is under attack. Your bottom tower is under attack.
Step right up.
Your top tower is under attack.
What's the ballyhoo?
Your top tower is under attack.
Take the show on the road.
Your top tower is under attack.
Unstoppable.
Scouting location? Wind me up. I'm the leader of this show. Getting in gear. Come one, come all.
Double
Your bottom
damage.
tower is under attack.
Let me go. Stay very, very still. Or don't.
Your bottom tower is under attack.
Wicked
Places,
sick.
people. Nothing would please me more.
The enemy's middle tower has fallen. Your bottom tower is under
This
attack.
circus travels. Step
Your
to it.
bottom tower has fallen. Dire structures are fortified.
I'll keep the lion tamer's share. Like a real boy. Ha! Nothing would please me more. Wind me up. Come one, come all. Who asked you? There.
Invisibility.
I think I can handle it.
Your middle tower is under attack.
Scouting location? What? No advance?
Your middle tower is under attack.
Proper blocking is paramount. Just because I can.
Dire
Triple kill.
Like a real boy.
Looking for me?
Don't worry, I never miss. My turn.
Ultra kill.
Pulling up stakes. Next stop, start. No, you can't leave now. Itchy feet.
Illusion.
Getting in gear. Over here. Everyone is over here now. This. Take the show on the road. Gather round. Hey, I'm under attack.
I'm over here.
Hands off. Hey, look over here. Let me go. No unsolicited material. One gear in front of the other.
Stupendous.
Places, people. What's the belly?
The enemy's middle tower has fallen.
Ah. I'm the leader of this show. There. Dialing up the violence. Proper blocking is paramount. Scouting location. Step to
The enemy's top tower has fallen.
Let the fun begin! You blew it!
I'm under attack.
Taste the what I miss!
Almost missed my kill under attack. Just because
Blown away!
The bottom tower is under
I'm the
attack.
leader of this show. Go on, show me a trick. Who asked you? Come
The
on,
enemy's
come
top
on.
tower has fallen.
Places, people. What? No advance? Nothing would please me more. I said dance. Pulling up stakes. Step right up. One gear in front of the other. Perfect.
Double kill.
My pleasure. Where was I going with this? Itchy feet? Yes, yes. Like a real boy. Hold this. Time for taming. I don't have to take this. You can still perform when you're dead. Coming soon to a village near you.
Has fallen to the radiant.
Fresh meat.
This circus travels. Take the show on the road. I think I can handle it. What's the knives real? The knives are sharp and the teeth are real.
You're but a blot in the black grimoire.
Very nice.
Dire structures are fortified.
Fresh meat. Wicked sick.
Your storm was coming?
Monster kill. Triple kill.
Come on, come
The
on.
enemy's bottom tower has fallen.
No, you can't leave now. Where? Yes.
The enemy's bottom tower has fallen.
Don't you know who I am?
The top tower is under attack.
Perfect.
Your top tower is under
Just
attack.
because I said
Dire structures are fortified.
this circus travels.
Your top tower is under attack. The enemy's middle tower has fallen. Your top tower is under attack.
Thrill me.
The enemy's middle barracks have fallen.
I'm under attack. I'm the leader of this show.
The enemy's top tower has fallen.
Nothing would please me more. This is
The enemy's top barracks has fallen.
Get away from me, you gormless tool. Itchy feet?
The enemy's top barracks have fallen. You now have mega creeps.
Pulling up stakes. Who asked you? I think we understand each other. Scouting location.
The enemy's middle tower has fallen. The enemy's middle tower has fallen.
Blocking is paramount. Where do they all fit?
Radiant victory.
Every intelligent system, human or animal, learns by interacting with the world. We touch, look around, move, actively test hypotheses, and explore our environment. This is called sensory motor learning, and it's how we understand the world. We often hear that modern artificial intelligence is inspired by the brain, but the truth is, current AI is very different. Current AI systems don't learn through active interaction with the world. They're trained on massive static datasets. Like being shown a photo album without ever touching or exploring the objects in the pictures, or reading all the text on the internet without knowing what the words refer to. At their core, they are just strong pattern recognizers. Humans learn in a much more flexible, efficient, and robust way. We don't need thousands of examples to learn something new. Think of how quickly a child can learn a new word, or how you can perform a new task after watching someone just a few times. We also don't stop learning once we finish a specific task. We always absorb new information and refine our knowledge. Imagine machines that could learn like we do, that interact, sense, and adapt in real time. This could solve many real-world challenges where internet-scale data isn't available or quick adaptation is required. This is what the Thousand Brains project is all about. At Numenta, we spent many years studying the brain and figuring out the principles underlying our intelligence. Now we're building an open-source AI framework that runs on these core principles. It's a fundamentally different approach that will change the way we think about AI.
Okay, we are going to get started here. So thank you very much for turning up in whatever time zone you're in. I know a lot of people are in a work day right now, so we really appreciate you coming to join us live. We think this is going to be an exciting presentation. So let's get started. So quickly, the agenda, go through some welcomes and introductions, and then Jeff's going to give an overview of the Thousand Brains theory, and Vivian Clay and Niels Ledong will be showcasing the implementation, the works so far, and then I'm going to go over how you can get involved in the kind of the community ecosystem out there. And then we're going to have a Q&A session at the end. So that's what's on plan. And so let's jump in. So a couple of administration points. This meeting will be recorded, as we just mentioned, and we will be putting this on YouTube, so you'll have access to everything. So if you do have to leave halfway through because you're at work, that's totally fine. You can submit questions throughout the presentation through the Q&A feature by clicking on the little Q&A button in your Zoom toolbar. And we may address some of the questions as they come up, and we may hold some of them till the end. Just depends on whether we can answer them quickly or not inside the Zoom chat. So please feel free to post questions all the way through. And with that, we'll start with some introductions. Okay, so if you're on this webinar, probably you know Jeff Hawkins. He doesn't really need an introduction, but I'll do my best. So Jeff founded Numentor about 20 years ago. He has devoted his life to understanding how human intelligence works. And he has 2 seminal works on intelligence and 1,000 Brains Theory. These books, I highly recommend them, kind of define and refine intelligence, what it is to be intelligence. And this is kind of his life's work. He won't talk about some of the other accomplishments in his life. So he invented the Palm Pilot, he founded Palm, he founded the Redwood Neuroscience Institute, he invented the graffiti language, recognition language. And these are kind of those side projects that got us here. And so this is Jeff. Next, you'll meet Dr. Vivian Clay, who is the director of the 1,000 Brains Project. She holds a PhD in computational cognition from the University of Osnabrück. And she's won so many awards, I'm not going to list them all, but just a top 3. So the Mendeleev Fairset Data Award, the IT Talent, Lower Saxony for a master thesis, the award for extraordinary master thesis awarded by the Rosen Group, and so on. So this is Vivian, and you'll hear about our current project from her later on. Then we have Niels Ledong, also a doctor, in this case, an actual medical doctor who graduated from the University of Bristol. But he found that being a doctor wasn't challenging enough, so he went back and got a PhD in neuroscience from Oxford, and Niels is our lead researcher here at the 1,000 Brains Project. Just a quick shot of the rest of the team. So this is a candid shot where we captured everyone thinking about something. We're not sure what we were thinking about. That has been lost in the mist of time, but everyone has a very thoughtful face on here. I'm Will Warren. I'm down here on the bottom center. So I'm the community manager for Numentor and your MC today. And then honorable mention for Tristan, who wasn't in the screenshot because he was off camera. He says he was probably eating at that time, but Tristan is also a member of the team here. Okay, and with that, I'll hand it over to Jeff and we can get started. So Jeff, whenever you're ready.
Jeff, you're muted.
Sorry about that. Am I visible? I see, I'm seeing the, okay, great. So anyway, thank you everyone for being here this morning or evening or wherever it is. Whether you're here live, hope that'd be nice. If you're watching this some future date on recording, that's great too. We appreciate you taking the time to learn about the 1,000 Brains Project. We're pretty excited about it. As you probably know, but it's worth stating again, the 1,000 Brains Project is a new open source project for creating a new type of AI technology based on brain theory, and really sort of replicating how humans and other mammals think and understand the world. As Will mentioned, it's been undergoing for many decades, actually, and it's a combination of several decades of research, primarily at Numentor for the last 20 years. So it's we call it sensory motor learning. I will explain what that means. I'm going to give you an introduction to the theory, but I just thought, well, let's just jump right into it. I'm going to give you an introduction to the theory. So I'm going to share my screen here, and I'm going to start with a few quotes. Hopefully everyone can see that. Let me make the presentation here. You know, brains work in very different principles than any kind of machine learning technology we have today. And, you know, 20, 30, 40 years ago, we didn't know what those principles are, but now we do. And we can say definitively that brains work on very different principles. I'm going to tell you to in a moment. And it gives us the perspective that today's AI technology is really, in our view, is as exciting as it is and as powerful as it is. It's not really on the path to artificial intelligence, true intelligence. We believe that the correct way to do this is to really understand what those principles are by studying brains, and we're going to share those with you today. So we're not the only people who feel this way. So here's some quotes from other people who've basically expressed similar concerns or feelings. And and I'm not going to read these to you, but I think we have a proposal and an alternate view for how to build intelligent systems, and that's basing them on the way the brain works and sensory motor learning. So let's just start with an overview of all learning systems. It's a very simple way to do this. All learning systems, whether they're biological or machine learning systems, have the following structure. They have some sort of training data that's fed into the system. The system learns a model of the data. We often refer to it as a model of the world, but it really isn't. It's just the model of the training data. And then the model is used to generate an output, whatever we want the system to do. Historically, the AI world has focused on the output. We've judged the success of our systems by what they do. How well can it label images, or how well can it translate languages, or how well can it play a game like Go or chess? And how the system works internally, although important, was secondary. A few years ago, convolutional neural networks were the hottest thing, and now transformer deep learning networks are the hottest thing. So whatever got you the best result was really mattered. But this is not really the way to look at it. If we want to understand if a system is truly intelligent, or what it will be capable of doing, or what its risks are and rewards, really understand what is going to happen in the future, we have to look at the other parts of the system. How the training data is collected, where does it come from, and how does the model represent data? We can think of this. There's an analogy in the computer world. When we think about what's a computer, we don't look at what the computer does. We say computer is something that has a CPU, memory, program, data storage, and things like that. And then we call it a universal Turing machine or a computer, and it can be applied to all kinds of problems, large or small. Well, I think in the future, we're going to think about AI that way as well. The AI system is going to be defined by how they work internally. An intelligent system is going to be defined by how it works internally, and they can be applied to many different problems, some of which things humans do and some which we don't do. So let's talk about sensory motor learning, which is the core of the Thousand Brains project, which I'll show a little picture of a neocortex up there, just to remind you that. But brains are sensory motor learning systems. So what does that mean? First of all, the data we get that we feed into this system is coming from sensors that actually detect aspects of the physical world. So the primary sensors in humans are vision and hearing and touch. We have other sensors too. Other mammals have different types of sensors, such as electric field sensors and seeing in ultraviolet and infrared, things like that. But it's always about sensing some physical attribute of the world. And an output of sensory motor system is movement. That's everything that a human does is based on movement. My voice and my speech right now is really muscle contraction. So we have sensor data in and movement out. Now, there's an issue here. As we move through the world, the input on our senses changes. In fact, it changes very rapidly as we walk, as we turn our heads, as we touch objects with our hands and move them over the surface, and as we move our eyes several times a second. The sensory data changes completely. And the brain can't make sense of that if it doesn't know how it's moving. So sensory motor systems have to take account of how movement is occurring, how it's moving its body through the world, how it's moving its sensors through the world. And that becomes a second input to the system. I'm showing that here in red. So we have sensory data coming in, the features of the world, and we have how the body is moving, how the sensors are moving through the space. Internally, what's going on in the brain and sensory motor learning systems is that this is stuff that the research has shown. So not everyone understands this. If you follow our work, you might, but not everyone understands this yet. That internally, you have a sense of location. The system knows where the sensor data is coming from, where it is located relative to something else in the world. We refer to that as a reference frame. So there could be reference frames relative to objects you're touching, reference frames relative to the rooms you're in, reference frames relative to your body. They're basically all information that comes into the brain is associated with some location in space. And how models are learned is by associating features with location. And so as you move your fingers over an object, or you turn your eyes and look at different aspects of a scene, your brain is essentially associating what you're seeing with where it is. It's really obvious. If you think about it, it's obvious to observers. When you just look around the room, you know where things are. That seems so simple, but it turns out that's not so simple. The brain has to calculate that, and it has to represent that internally. And so you're constantly just matching features of location. In a very simple, specific example, you can think of it like this. Here's a tip of a finger. Let's say you're imagining you're touching this cup with the tip of your finger. As you move your finger over the surface of the cup, maybe on the rim, you might feel an edge or curvature. You might feel a texture. That's the sense feature. But as your finger moves, the brain keeps track of where it is in space. And therefore, it's able to build a three-dimensional, basically, model of the cup. It's very much like CAD model. This is actually going on in your brain all the time. So we build models of things, in this case, a model of a cup, by just associating what was sensed where. And the movement of the sensor is actually fed in, and it's updating this location in a reference frame using a system called path integration. It basically says if it knows where it is and it knows how the finger is, what direction it's moving and how fast it's moving, it can update its location, much like Dead Reckoning, and if you know what ships used to do. All right, so now this just shows an example of a single fingertip And this finger, in your brain, your single fingertip could learn a model something like a cup. I could literally put your hand in a black box and you could feel around with a single fingertip and build a model of something by moving it like that. But let's now turn to brains, because brains are actually, they do this in a very interesting way. I guess I should mention this before I go on. Just in summary, we learn by moving and sensing and moving and sensing, and knowledge is represented by associating observations with locations and reference frames. And this way we learn structured models of objects, places, and concepts. By the way, it's easy to imagine how you can learn models of objects and places this way. It's a little bit harder to model how you learn models of concepts like mathematics or democracy or language. But as we'll see in a moment, this is how the brain does it. And although we don't understand all of it, it's very clear that it's using the same method for knowledge representation for everything that humans and other mammals do. Okay, now if we look inside this one neuroscience slide here, if we look at your brain, this is a picture of the neocortex, which is about 75% of your brain. It is the organ of intelligence, meaning all the things we associate with intelligence, from basic perception of touch and hearing and vision to language, the thoughts and so on, all occurs in the neocortex. And it is, all mammals have a neocortex. Ours is particularly large, but all mammals do. They have the same structure. If you were to look at this structure in detail, you see it's actually a sheet of neural tissue. It's about 3 millimeters thick. It's about the size of a large dinner napkin, about 1,500 square centimeters. So you can imagine it's a large sheet. And if you could look and cut through that sheet, imagine now you're looking at these columns. They're being shown here, the thickness of the neocortex, which is about 3 millimeters thick. The neocortex is composed of these columns. They're called cortical columns. They're about 1 millimeter in area. We might have quite a few more than these. No one really knows. You can't actually see them like this in the brain, but we know they're there. The neuroscientists have a way to determine these columns there. And the structure of these columns is nearly identical everywhere in the brain. So if you look at anywhere in the brain, you see the same column structure in the same detailed architecture in each column, whether those columns are doing touch or vision or hearing or language or anything else. Your brain is made up of copies of the same basic neural circuit over and over and over again. And other mammals have the same column of structure. They just have fewer of them than we do. All right, so it turns out that in the brain, those cortical columns are mimicking exactly what I just talked about. Each cortical column is a sensory motor learning system. Each cortical column builds reference frames and builds models by movement and features coming in. So in the Thousand Brains project, we call these learning modules. And so you'll hear the term learning modules throughout the presentation today. They're equivalent to what's going on in the brain in a cortical column. So it's a highly distributed system, 150,000 a minimum in a human of these sensory motor learning systems. This is the primary reason we call this the Thousand Brains theory and the Thousand Brains project, because we have lots of these little things that are just like little brains, but they're just replicated. And by the way, the human brain got large by making evolution decided to make more copies of this basic circuit. Okay, so how do these things work together inside? This is kind of tricky, but this diagram will illustrate it. Here in this image, you're going to see more of these images later. We're representing, you can see there's, here I'm showing 8 of these learning modules, each one showing a little reference frame and a little box above it. They're attached to different sensors, which are represented by those little blocks on the bottom. And these learning modules are connected in 2 basic ways, 2 ways of distributing them. And we know this from brain research. One is that there are these lateral connections between learning modules that allow them to reach inference faster, and they lead to a unified perception. So when you actually look at something, there are thousands of these cortical columns in your brain, each looking at a part of the visual world, each looking at a part of the retina. Nobody looks at the whole thing. And so each one is able to infer what's going on through movement. But if they talk to each other, they can say, I think it might be this, and I think it might be that, and they can vote and reach a consensus very quickly. And this is why you can flash an image in front of somebody's eyes, and they can tell you roughly what it is, because these columns communicate with each other and allows them to reach a conclusion about what's going on without movement. If you didn't have this kind of voting, then they'd all have to move. It'd be like looking at the world through a straw or touching objects only with one finger. If you do that, you have to have a lot of movement to infer and learn. But if you do this voting, you can make inference much faster. The second type of communications between these learning modules is a hierarchical connections. And that's shown here. We're showing 2 levels of hierarchical connections. These exist in the biological neocortex. and they exist in the Thousand Brains project as well. And these connections allow the system to learn models composed of objects composed of other objects. And that's how the way that the world is structured. Words are composed of letters, sentences are composed of words. Cars they're composed of doors and windows and tires and so on. Wheels composed of tires and rims and so on. We learn this compositional structure by having these kind of hierarchical connections like this. Okay, so these are the basic ways you can build. The brain, biology has learned to build intelligent systems. Sensory motor systems built of these individual learning modules. Each sensory motor learning systems, they're replicated in various ways, and they're connected in both horizontal connections and vertical connections. And this is how you understand the world. Your brain is structured like this. Niels and Vivian will get into this later, but one of the beauties of this system is that it makes it so as we build intelligent systems, we only have to really figure out how these learning modules work. And then once you've got them working, which we have them to some extent, we do have them working now, to a large extent, you can replicate them and make systems of various types. You can apply them to various types of sensors. So it's a very, very flexible system. It'll give an incredible variety of AI or intelligent systems will be made this way in the future. I'm going to end with a few thoughts, just to get everyone excited, or at least on the same page, or at least know what page we're on. Machine intelligence is going to transform the 21st century, similar to how the computing transformed the 20th century. I think that's a really good analogy, and so we're just starting that. We're like 1940 or 1950 in the computing era. That's where we are in AI right now, and it's going to be really exciting and fast growth in this field, and it's going to lead to many, many benefits. I believe that sensory motor learning, and not today's AI, not deep learning or convolutional networks or transformers, will be the technology at the heart of this transformation. Not that those other techniques are going to go away. I believe we'll have transformer networks for a long, long time, and they'll be an important part of our technology. But I don't believe they will be the core of AI. What people in the future will think of as really AI will be based on sensory motor learning. And I should mention that it's also the core of robotics. This is how we're going to do truly robotic systems using these techniques. And finally, I believe, or at least I hope, this is more of an aspiration, I guess, is that the Thousand Brains project will be a seminal event in the creation of truly intelligent machines. As far as I know, this is the first place that anyone can really, we have all the material, we understand what's going on for the first time, we're starting to build this stuff for the first time, and this will really be the seminal event to do this. I guess I forgot to mention earlier, and I should do that right now, I don't want to forget this, that we've been working on this for several years. The theory has been going on for decades, but we have been working on the code for several years, mostly Vivian and Niels, and we proved that we can actually do this. So we're not starting from scratch. And if we come into the Thousand Brains project, you'll see there's a lot of code already, and a lot of stuff that's working, and a lot of documentation, and a lot of videos, and there's a lot of stuff to digest. It's not easy in the sense that the concepts involved here are new. There's a bit of a learning curve to understand these concepts. It's not like any other machine learning system you might be familiar with, but it's very rewarding, and it's fun, and it's very exciting. So I hope you find it exciting too. And I hope some of you, or all of you, or as many as possible, can help contribute to the Thousand Brains project. We put together a really great system. We're hoping to have a lot of contributors. With that, I'm going to pass it over back to, I guess, Will, who's the master of ceremonies here.
Thanks so much, Jeff. That was a great overview. Just to remind everyone on the call that you can go and ask questions in the Q&A section, and you can vote for other people's questions as well. I don't think I mentioned that, so you can upvote questions, and then the top ones will answer. And now I'll hand it over to Vivian for the next part of the presentation.
All right, thank you.
Your top tower is under
I'll
attack.
share my screen and slide control with you, Niels. All right, so Niels and I are going to talk about Monty, which is how we call our first implementation of such a sensory motor learning system. We call it Monty in reference to the neuroscientist Vernon Mountcastle, who first proposed this idea of the cortical column as a repeating general computational unit in the brain. And I just put this little link down here to make this point again, that this project has a very concrete implementation already, and it's all open source, and you can find it at this URL and take a look at the code yourself, run it yourself, or even contribute to it. Making this presentation was tricky because there's so much we could go into, and we could talk about every slide in depth. But this presentation, this meeting is scheduled for 3 hours, and still we're only going to scratch the surface. So, as Jeff already mentioned, it's a bit of a learning curve if you first come to this project, because we're not just taking an existing AI system, we're not just taking transformers and adding a little incremental improvement to it. We're really building a fundamentally different system, and that means to understand this, you're going to have to disband some of your preconceptions, some of the ways you currently think of AI. For example, thinking that you need a huge labeled data set or just a huge internet scale data set, and kind of start from scratch and have a fresh mind when you come to this project. And I'm going to repeat a few things that Jeff already said again, just because it takes some time for these concepts to sink in and for this approach to sink in and make sense. Again, like Will said, feel free to ask questions as I present this. All right, so what is a thousand brains system? The thousand brain system we call it that because it's based on the thousand brains theory, and as Jeff mentioned, it's called thousand brains because we have this idea of the cortical column, which is found in the brain as the general repeatable computational unit that can do a lot on its own already. And about 3 years ago, we took this theory and the principles in there that I outlined in Jeff's book and started building a system based on these principles. And we kind of proved to ourselves that this is really a good approach and this actually works. And now we decided to take it and make it open source and publish everything we found out so far. And it's been really exciting for especially Niels and me who've been working on it since the beginning, the past 2 weeks since we published all of this. It's just been so much fun to be able to talk about all these ideas and this really cool approach. So I hope you'll be excited too. So let me go through the key principles of these systems. First and foremost, it's based on sensory motor learning and inference. So as Jeff mentioned, everything is about sensing and moving, sensing and moving, sensing and moving. Both learning and inference is sensing and moving. And also the models that are being learned are made for this kind of data. They are models that are explicitly designed to model a stream of sensory motor input and to produce action outputs. How are they designed for that? One of the ways that you can model sensory motor data is using reference frames. So having an explicit representation of space, knowing how to path integrate in space. So if I go from A to B to C, I know how to get back from C to A, even though I never took that path. That's what you can use a reference frame for. And you can think of it as like Cartesian coordinates, for example. And as you're looking around a room, you can recognize objects and recognize where they are relative to each other, and you can remember that and model that using reference frames. And then the cortical column as the general repeatable functional unit. Each of these columns can learn full models on its own. So it's not like it just implements an edge detector or detects some kind of pattern or texture. It can actually model entire three-dimensional objects. And it doesn't actually sense the object all at one time, but it slowly moves, it can move over the object and then build a model of that larger object and recognize that object. And that's why I put this sub-point here, because this is a concept that I thought when I first came to this project was a bit hard to sink in. If you come from computer vision, you always think, oh, I'm going to give this photograph to my AI system and it will process this picture. But really, if you look at the brain, there is no full image anywhere. You have the retina and the eye, there are tons of blood vessels going around everywhere. There's the optic nerve exiting here, where you have actually a blind spot that you don't even perceive. You have neuron bundles going through the LGN, left and right visual field being separated. And each of the neurons in V1 actually perceives a very small part of the visual space. So if you look at your laptop, a neuron in V1 actually has a receptive field smaller than just a couple of millimeters. And so each of these cortical columns always just sees a tiny patch of the input. and it doesn't get the entire image, but instead you have to move around your eyes saccade about 3 to 4 times a second and move around and recognize things that way and learn that way. And then lastly we have what we call the cortical messaging protocol, which is essentially a way of saying that all of these columns, no matter if they model touch or vision or abstract concepts, they can communicate with each other using a common language. And this makes it really easy to kind of have multimodal systems and to scale the system, stack these on top of each other, and I'm going to go into more detail on that as well. But I just wanted to outline these principles again. All of them Jeff also touched on already, but it's really good to keep these in mind. These were our compass for the past 3 years when we built the system, and every design decision we made, we thought, does it follow these principles? Because looking at the neuroscience literature really showed that this is what the brain's intelligence is based on. And so we try to always keep these key principles in mind when building Monty.
What? No advance?
All right, now I'm going to go into the actual implementation and concepts there, and I'll start with the cortical messaging protocol because it's really the glue that holds the whole system together. So we start by defining what a message needs to contain. And the key ingredients here are, it needs to contain a pose, which is basically a location and an orientation in a common reference frame. That could be relative to the body, or it could be relative to some external point in the world, but some common reference frame. And then it can contain a list of features, for example, color or amount of curvature that's being sensed, whatever that sensor is sensing as features at that location. And additionally, we can have some auxiliary routing information like a confidence or sender ID for some of the routing within the system, which is a bit more technical part. And this messaging protocol is used everywhere inside the Monty system. So, for instance, we have the sensor modules, which get the raw sensory input, and then they output an observed state adhering to this messaging protocol. So it could output, I'm sensing this location and orientation up here, and I'm sensing red and the curved surface. This goes into the learning module, and the learning module tries to infer what larger object it is actually sensing, and then outputs this as the hypothesized state. So it might output, I'm sensing a red coffee mug in an upright orientation. It can also communicate possible objects laterally to other learning modules to speed up inference. Again, using exactly the same format of pose and features. And lastly, the learning module can also output goal states to the motor system, telling the motor system how it wants it to move. What does this kind of messaging protocol give us? First of all, it gives seamless multimodal integration. So learning modules that learn to model touch input can easily communicate with those that model vision input, or those that model LiDAR or ultrasound or any other modality. Doesn't matter, they can communicate with each other because they follow that protocol. It also allows us to easily model compositional objects. So whatever object and pose this learning module recognizes can just become the input to the next learning module. The coffee mug that's recognized down here just becomes a feature in the model of this learning module. And they don't even need to know where in the hierarchy they are. It doesn't matter for the learning module whether it gets input from a sensor or from another learning module, because it's all just in the format of features and poses. And this makes the system very extendable and scalable. So if you have a very simple application, you can just use one learning module and one sensor. And you can do a lot with that. Actually, when we implement the system, for the past years, we've mostly just used one learning module. And one of these units is really powerful on its own already. But if you have a large application or you have tons of sensors and they all need to communicate with each other, you can use thousands of these, and you can easily scale them to whatever your application requires. It's not like a transformer where you need billions of parameters to do anything useful. You can do a small solution with one or just a few of these modules, or you can scale it for tons of sensors, or scale it up in depth for modeling more hierarchical compositional concepts.
Nothing would please me more.
It means that it's a very nice plug-and-play framework, and I'll go into some more detail on that in a bit as well. And it also makes it a very distributed and parallelizable system. So you can use a very quick associative local learning in each of these modules themselves. You can run all of these individual modules in parallel. They don't need to wait on anything. They don't need to process anything in serial. And that way it can be implemented quite efficiently. All right, that's the messaging protocol. Now to the two core components that I already mentioned, sensor modules and learning modules. So the sensor modules, as I mentioned, they always see a small part of the object and they move. So here we're seeing a coffee mug. This is really just for visualization. The sensor module just sees a small patch of the object. So you can imagine like the tip of your finger moving over an object or a little patch on your retina. And then the main job of the sensor module is to turn raw modality-specific data into the cortical messaging protocol. So for example, if you have an RGBD camera, the camera sees this patch. You can extract a point cloud from that depth image. From that you can extract a location relative to the body or the camera or the agent or some external point of reference. And you can extract a rotation. So we usually define that by the point normal that points out of the surface and the two principal curvature directions. And then you can extract some other features as well, like what color is sensed here or the amount of curvature that's being sensed. And this is then in the correct format to send it to a learning module. Important thing to say again, the sensor module needs to be able to extract a pose. Otherwise you can't send something in the format of the cortical messaging protocol. So it needs to somehow be able to extract pose or movement information. It can be done in many ways. You could actually get a copy of the motor command, or you could extract it from optical flow or proprioception or other signals. And then the learning modules, that's really the heart of the modeling system. So the purpose of the learning module is to model incoming streams of poses and features using reference frames. And using reference frames means we're not just, the model is not just a bag of features, it's features at poses. So let's say we have a car and we first look at the tire and then the door and the hood of the car. And we sense those as features, but we associate these features with locations in a reference frame of that object. So the tire is at a relative location to the door, and the door is at a relative location to the hood of the car. And that really defines the car. And this is what we inferred from looking at the neuroscience and what the neocortex is doing. So the whole structure of the learning module is very heavily inspired by the structure of cortical columns in the neocortex. So if you take a slice of this neocortex anywhere, you find this layered structure of different types of neurons and cells. And this structure is found everywhere across the neocortex, and it's remarkably similar everywhere. And we spend a lot of time looking at the neuroanatomy and the physiological studies and what we know about the neocortex by now. And you can draw some analogies between how we implemented Monty and what's happening in the neocortex, although we don't always explicitly talk about it in the code, but just as a bit of background. So in our current implementation, the learning module that we use most frequently is called the evidence-based learning module, and I'll just give you a quick overview of how that actually works at a high level. So we have a sensor module which converts the sensory input into the messaging protocol, which means we get features and pose, and we get a displacement, which is like a movement in space. And then it also produces a motor output, since it's a sensory motor system. And since it's interacting with the world, this happens over a series of steps. So each motor output leads to a new sensory input, and that gets processed, integrated again, leads to a new motor output, and so on. As we get features and poses as input, we have some hypotheses in memory, and we can update the evidence for those hypotheses. So let's say we have 4 objects in memory. We are modeling these as features at locations. And as we're getting feature inputs and movements, we can say how consistent these the series of features and locations is with our models in memory. And for example, here we might have gotten some features and movements that made this bowl very unlikely, and all these cylindrical objects are still likely, but then even within an object, some locations are more likely than others. And the most likely of these hypotheses becomes the kind of hypothesized pose and idea of the object. So for instance, a coffee mug and an upright orientation and location relative to the body. And this would be the output of the learning module, which could become the input to another learning module, or it would just be the output of the system if we do simple object and pose recognition. We can also share this information with other learning modules laterally to come to a conclusion quicker in a process that we call voting. And then lastly, we can also have model-based policies where we use these hypotheses to generate goal states and tell the motor system how to move next, and Niels will go into more detail on those. And to see the system in action, I put an animation in here that I'm just stepping through very slowly to explain this a bit more visually. So basically we have a little sensor patch here that moves over a coffee mug. This zoomed out view is just for visualization. And we move down the coffee mug and then on the bottom of the mug. And with every step, we update our hypotheses. So by this time, we already decided it can't be the banana, very low likelihood. The dice, way too small. The bowl, also not very likely. And then on the coffee mug, most locations on the mug are also unlikely, but there's this little red ring, red means highest likelihood, that goes around the coffee mug at about the height of where the sensor patch is right now. And this is where we think we most likely are. We can't really determine yet where around that coffee mug we are, but once we get some more distinct features like the handle, we can be pretty sure of where we are and what object we are sensing. And this will be eventually the classification. And importantly, we always have a most likely hypothesis. We don't need to sense the entire object to be able to say anything, but we always kind of have a working hypothesis, and we update it with every step and refine it with every step. And just another example with another object. Here we have a dice, which is a bit smaller, so we're moving on the dice, and since it's so small, we very quickly rule out these larger objects. And then on the dice, we have lots of evidence. And since it's such a symmetrical object, it's a bit harder to nail down how it's actually rotated. And the system can recognize this, actually. It can actually recognize that there's some symmetry. And then in this case, it actually detected a rotation that's not the rotation we showed it, but it's basically the same look. So it detected that it's symmetric. And this is kind of what we would want in a system. We wouldn't want it to rely on these tiny artifacts on the dice. And yeah, that's how the system works. Moving, sensing, updating hypotheses, moving, sensing, updating hypotheses. And at every step, we have a most likely hypothesis of what we're sensing. And this was all one sensor and one learning module, but we can also use more of those and then vote between them. So we could have 5 patches that are sensing different parts of the mug and moving across that mug. And we connect each of these patches to a sensor module, and then the output of the sensor module goes to 5 learning modules. And since they all get different input, they might have different hypotheses. So they might think that they are on a different object, or they might think that they're on the same object but in a different orientation. But we can quickly resolve this by sending these lateral votes, and then narrow down which object is being sensed much quicker and more robustly as well. Okay, now this one is a bit of a complex figure, but I think it just kind of puts everything into one image, so bear with me. Again, the 3 components here: learning modules, sensor modules, and motor system. Here in this example, we have actually 2 sensors. We have an eye and a finger, and the eye is sensing 2 parts of the mug, and the finger is touching the table here. Each of those patches go into a separate sensor module, and the sensor module extracts features. So we might extract blue for the ones on the mug, and then a flat surface for the touch sensor on the table. And then these features and poses go into learning modules, which then, through successive movement, build up hypotheses of what they are currently sensing. So ideally, these 2 would sense a coffee mug and recognize that, and the finger, after moving a bit, might recognize that it's sensing a table. And then these again, since they're following the protocol messaging protocol, can become the input to another learning module. And that learning module might learn a compositional scene of the coffee mug standing on the table, which are again relative locations. So a coffee mug on the table and the mug and the table then become features in that compositional object. Additionally, we might also have skip connections, so we might directly send the output from the sensor module to a learning module. We also have these lateral connections for voting and quicker inference. We might have top-down connections, so if we've already recognized the dinner table scene, that might bias the lower-level learning modules to quicker recognize what's on the table. And then every learning module has a motor output. This is, again, something that we also see in the brain, that we have outputs to subcortical motor areas everywhere across the brain, not just from motor cortex. And those go to the motor system, which then translates it into actual motor commands. And so all the dashed lines don't need to follow the cortical messaging protocol. The motor system and sensor modules are basically the interface between Monty and the world, and they translate back and forth between the raw data and the cortical messaging protocol that's used everywhere within the system. Okay, so the Monty, now actually to the code. So this is the Monty framework. If you go to our code base, you might find some abstract classes with exactly these names. And that's how they relate to each other. This is a bit of a simplified view. So we have a Monty experiment, which an experimenter can use to kind of set up the framework of what you want to test and what kind of task you want Monty to do. And you have Monty, which can have as many sensor modules as you want, as many learning modules as you like, and a motor system. Monty kind of manages how the sensor modules connect to the learning modules and how the learning modules connect to each other, and that information routing is managed in Monty. And then we have the environment. Right now this is a bit more complicated. It looks more like this, but we plan to simplify that. But basically we have an environment, and there's a bit more detail of the learning module actually having memory and having object models as well. And the core idea is that you can customize each of these classes individually without changing any of the other classes, and kind of plug and play and compose a Monty system however you like. You can use as many sensor modules or learning modules as you want. You can connect them however you want, but then you can also write custom classes for each of these boxes. And for instance, you can write a custom sensor module for a sensor that you have, plug it into this framework, use exactly the same learning module, motor system, environment, and so on, and just test a different sensor. So for instance, we have a distance sensor that's kind of like an eye moving in a socket. We have a surface sensor that moves like a kind of a hand. We have a sensor module that only sends a message when features change significantly. We can mix in some noise for experimentation. But you might implement your own sensor modules, like one for sound, or LiDAR, or ultrasound, or whatever you might think of. You can also customize a learning module. So for instance, a lot of our work we've been doing with a graph learning module, where we use explicit graphs to model objects, because this makes everything very easy to visualize and to debug, and for us to kind of figure out all the plumbing in the system and what's actually going wrong exactly when something doesn't work. And we've went through several iterations of different learning modules, starting with a displacement learning module where we use displacements to recognize objects, moving to a feature learning module where we actually look at the nodes in the graph instead. And then now the current, I would say best version, the evidence graph learning module, where we actually keep track of continuous evidence values for different objects and poses. And they all have their strengths and weaknesses, generally getting better from left to right. But it's just been very easy to plug in different types of learning modules and compare them while leaving everything around the same. We also played around with the learning module using some of Numenta's previous work, the hierarchical temporal memory, in combination with simulation of grid cells. You might think of actually implementing a neuromorphic learning module, doing something in hardware. As long as it adheres to the interface that we defined for the learning module, you can do whatever you like inside the learning module. Of course, it should be kind of built for modeling sensory motor data, so a reference frame inside a learning module is very useful. But if you have that, you can kind of replace these, leave everything around the same. And you might come up with other approaches than our evidence graph learning module, and we might come up with other approaches in the future. Then you can also customize the environment. So in this case, the data loader and dataset. We often work with the habitat simulator, which is like a 3D simulation engine. We also implemented a real robots environment as a simulator. We have an omniglot environment, which basically you kind of trace the strokes of different handwritten alphabets. We have one where you saccade on an image, basically moving a little patch across to the image. And then for datasets, we often use the YCB datasets, which is like 77 household objects, and render them in Habitat. Recently put together a scene dataset where it's 3D objects relative to each other arranged in a scene. We have a dataset of real-world images. And then, of course, you can think of tons of different ways you could test the system. And then lastly, the Monty experiment kind of defines how you put Monty into the environment and how you measure performance and all this. So a lot of the times we've been looking at object recognition, but we've also looked at generalization, supervised training. Profiler is just useful for optimizing the system, but you might think of tons of other ways you could experiment: object manipulation, washing the dishes, mapping an area, detecting problems. I mean, the general idea is just that this is a core algorithm that applies to a huge range of areas. And this framework easily allows you to do that. And I hope this was a little bit inspiring and gave you some ideas maybe of what could be interesting to test, or which component you would find interesting to test out or replace or try something, try a new environment. And with that, I'll hand over to Niels now.
Nice. Yeah, thanks very much. Great. So yeah, I'm going to be talking about motor policies in Monty. And I just thought it'd be useful to kind of take a step back, because you've heard a lot about kind of 1,000 brains. So you have all these different learning modules, which are each developing explicit structured models of objects in the world, and they communicate with one another and are semi-independent to a certain degree. And so, those are the 1,000 brains. You've also heard a lot about how the system is sensory motor. But I think it's really worth emphasizing, although this was touched on earlier, that each learning module, each component of the system is a fully sensory motor system in its own right. Because that's a really key concept to how it's going to operate and how it's going to kind of act in the world. And this was, as Vivian alluded to, very much inspired by our knowledge of the brain. So I'm not going to go into, obviously loads of neuroscience detail, but just briefly, if you look at this view of the cells in a cortical column, which again, maps onto the learning module, there's this distinct layer that projects to the parts of the nervous system, the subcortical parts that control the body. And you may have kind of come across the concept of a kind of motor cortex and have this impression that that's the part of the brain that controls how you move, and then everything else is relatively inert as opposed when it comes to kind of motor control. But that's not the case. So anywhere where neuroscientists have looked for these cells, they have found them throughout the neocortex. So it's the entire organ. It's every cortical column, and therefore in our implementation, every learning module that is sending this motor control throughout the system. It's also worth kind of emphasizing this because this is very different from how sensory motor control is implemented in any AI systems that do have sensory motor control today. It's a very different approach to have such a highly distributed, kind of semi-independent collection of units providing the sensory motor control. So I thought that was kind of a useful perspective to just kind of recap on. That's talked a lot about kind of motor control and how the system's acting, but what exactly is being controlled? So if you look at our kind of documentation and our code, you'll see this concept of agents come up, and we were showing the example of this kind of eye in this hand. And essentially what we mean by an agent is just a system that can move in a semi-independent manner from another system and has sensors associated with it. So a good example is something like an eye that can move around at least relatively independently from a finger, and both of them have sensors associated with them. And specifically in our code, we refer to two things, a distant agent and a surface agent. And roughly speaking, the distant agent maps onto what you'd think of as an eye or a camera that pivots around, and the surface agent roughly corresponds to a finger or a robotic digit that would sample an environment. And so, for example, the distant agent can rapidly look around a scene and depends on sensory information that can propagate freely through space. So, light being the clear one. Whereas the distant agent the surface agent needs to close the space to the objects it's sensing in order to sense them. But this confers additional advantages like additional sensory modalities and, for example, being able to manipulate the object. It's also worth highlighting, though, that ultimately this distinction is a bit of a false dichotomy because, as we move away from biological systems to artificial systems, whether that's in simulation or something like robotics, of course, we have a bit more flexibility. Cameras are very cheap. And, you can imagine, for example, a robotic arm that also has cameras that are able to sense things like color on the actual appendage. But that hopefully gives a bit of a flavor of, when I'm going to talk about policies now, what exactly is being controlled. And so going to then policies, this really refers to how the system, given the current state of the environment and of itself, how it decides to act in the world. And you can imagine that a policy could have a variety of kind of focuses of what it's trying to achieve. A clear, important one is just inference, so recognizing what you're seeing and where it is in the world. But you could also have a policy that's focused more on learning. So how do you efficiently gather new information in order to build new representations? And thirdly, you could have one with manipulation as the core focus, where it's all about how you can, change the environment. But our aim right now, or kind of our focus so far, has really been on the inference side and to a lesser degree with learning. But all of these are going to become something that we explore in the future. And so when you talk about policies, there's two real ways that you can break them down and structure them. The first is what you would call kind of model-free in AI terminology, and I'll get into this in a moment. And the other one would be model-based. And so in Monty, the model-free system is really referring to this part kind of early in the architecture where you have this sensory information coming into a sensor module, here circled in purple, and then being sent to a motor system, and then you have an action output. And this is called model-free because this circuit can operate, or in fact does operate, without building any explicit models of what exists in the world. And this is, and this is kind of represented by the fact that the learning modules further down in the system aren't involved in these kinds of decisions. And this is, analogous to how the subcortical structures in the brain can help us carry out actions without needing to involve the kind of more deliberate cortical thought processes. It's also worth mentioning that although this is kind of a model-free system and doesn't have explicit models, it can firstly still learn, and for that reason, it can also still be quite powerful. And it's definitely an important part of how the system can efficiently interact with the world. And so when Monty kind of first opened its eyes, so to speak, it would just kind of randomly move around on the surface of an object, just performing these kind of small saccades. But already in the beginning, we began implementing these kind of simple, you can think of as innate model-free policies. Like if you move off of an object that you're looking at, and are just kind of looking into the distance, try and move back onto that object just to get a bit more of a sense of what exactly it was you were seeing that's near you.
Take the show on the road.
But then we began implementing some more sophisticated policies. So for example, for the surface agent, there's this policy that enables it to move onto the surface of an object, and then using the information that's coming into it. So again, it's model-free. It's getting sensory information, but without having an explicit model of, say, I'm sensing a coffee bug. Use that information to then make movements that keep it on the surface of the object and enable it to explore the surface. But in of itself, this process is going to either result in the agent just kind of moving in a straight line, kind of looping around the object, or just moving randomly without any kind of deliberate kind of goal. But a kind of early then model-free policy we can do to make this a bit more deliberate is introduce this kind of curvature following. And so this is something that we already have implemented, where in an object like something like a coffee mug, you have these dominant curvatures that exist at any kind of point on the object. And this is something that when you're feeling the surface of it, you can sense. But these kind of dominant curvatures give you some sense of kind of where are interesting features, or where kind of is the object changing in an interesting way if you follow them. And so again, kind of without the system needing to know what the actual shape of the whole object is, if it just senses these curvatures and decides to follow them, it tends to efficiently explore interesting things like the rim of the coffee mug or the handle. And so this is showing that in practice, where if you imagine the kind of agent is starting at the bottom of the mug, which is upside down, and then it's moving down along its side. But when it reaches the rim of the cup, it kind of senses this quite strong difference in the curvature, and then decides to kind of follow along that. And so it's kind of looking for essentially just interesting features that it's coming along. I should perhaps mention that so far these model-free policies are, I think alluded to earlier, kind of innate policies that we think are important for the system to be able to efficiently interact with the world. But you can also learn model-free policies, and that's something we're also exploring. And any kind of learned policy can, of course, leverage whatever innate policies there might be as a kind of primitive. But what we're really excited about is model-based policies, because this is really where kind of true intelligent action comes in. And the name model-based comes intuitively from the idea that the actions that are being proposed, as Vivian mentioned, we call them goal states because it's really a state that you want the world or another object to be in. Those goal states are being informed by an explicit model of the world that a learning module has. And as you kind of see again with these pink arrows, every learning module is going to project these kinds of goal states around the system in order to try and influence the state of the system and therefore the state of the world. And whereas the kind of model free was analogous to the subcortical structures, this is analogous to the kind of more deliberate, thought out action planning that your cortex enables. And one of the reasons we're excited about this is because model-based policies in general are a major challenge, but something that is kind of a key goal really in artificial intelligence in order to act intelligently. And it's something that mammals do very well. And where there has been, for example, success in AI with AlphaGo that was able to defeat Lee Sedol in 2016, a key part of the success was actually providing an explicit model in the system of the structure of a Go board. However, in the real world, we don't have the kind of explicit structure like that just available, and it's not some kind of simple mathematical object that we can just inject into the system. And so if you imagine in kind of a complex setting where a family is cooking, there's a huge array of different objects that are there, each with their own complex behaviors, their own complex structure, and different ways that they can interact with one another. And so in order to act intelligently using these explicit models, the system first needs to actually learn the structure of all these objects. And so one policy that I can tell you about that we already have implemented, which is a model-based policy, is what we call this kind of hypothesis testing policy, because it's really a way for the system to, given the knowledge of the objects it knows and given what it's sensing, propose somewhere that it can sense in the world to efficiently disambiguate between what objects it's seeing and also what their kind of pose in the environment is. So if you imagine on the left, these are the known objects that the system has. It's experienced before. It has a model of a spoon, a knife, and a fork. And on the right is the observation that it's experiencing. So it's kind of moving along the handle of the spoon. But what we want for the kind of system to do is, having just observed the handle and therefore being uncertain about which piece of cutlery it's observing, we want it to kind of intelligently be able to understand that the place to move to disambiguate these hypotheses is the head of the object, in this case the head of the spoon. And unfortunately, I don't have time to kind of go into detail about the algorithm today. But at its core, what this is doing is taking the models that the learning module has developed through learning, transforming them by the information that it's receiving, its understanding of the state of the world as it is now, and then comparing these representations in a way that it can propose where these kind of objects would be most different if they are both present in the environment. And so seeing this in action, if you imagine